A complex valued function f defined on an open set U subset of calligraphic C is called complex differentiable at a point z0 in U if the limit f prime of z0 equals limit as h approaches 0 of f of z0 plus h minus f of z0 all over h exists and gives the same value no matter how the small increment h approaches 0 in the complex plane. Think of a smooth hill. The steepness, the slope you feel when you take a tiny step should be the same whether you step north, east, or any diagonal direction. If this directional independence holds at every point of an open region, the function is called analytic or holomorphic on that region. Analyticity is stronger than ordinary real variable differentiability. An analytic function can be expressed locally by a convergent power series. F of z equals sum from n equals 0 to infinity of a sub n times open parenthesis z minus z0 close parenthesis raised to the n. So the function is infinitely differentiable, and its behavior is completely captured by its Taylor coefficients. Write f of z as f of z equals u of x comma y plus iv of x comma y, where z equals x plus iy, and u comma v map from double struct r squared to r. The requirement that the complex derivative be independent of direction translates into two real equations known as the Cauchy-Riemann (CR) equations in Cartesian form. Partial u with respect to x equals partial v with respect to y. Partial u with respect to y equals negative partial v with respect to x. These equations say that the rate of change of the real part u in the x direction must match the rate of change of the imaginary part v in the y direction, and similarly for the other pair, ensuring a perfect twist between u and v. Example, for f of z equals z squared, we have u equals x squared minus y squared, v equals 2xy. Computing the partials gives u sub x equals 2x, v sub y equals 2x and u sub y equals negative 2y, v sub x equals 2y, so both CR equations are satisfied, confirming analyticity. Explanation: sometimes it is convenient to describe points by radius r and angle theta, polar coordinates, where z equals re to the I theta. Let f of z equals u of r comma theta plus iv of r comma theta. By converting the Cartesian CR equations, we obtain the polar form of the CR equations. Partial u over partial r equals 1 over r times partial v over partial theta, and partial v over partial r equals negative 1 over r times partial u over partial theta. These relations capture the same twist, but now in terms of how the function changes radially versus angularly. As an illustration, consider the exponential function f of z equals e to the z equals e to the r cosine theta times the quantity cos of r sine theta plus I sin of r sine theta. Computing u and v and their r and theta derivatives shows the two polar CR equations hold for all r greater than 0, confirming that e to the z is analytic everywhere. The CR equations give a necessary condition for analyticity, but they are not enough on their own unless we also assume the partial derivatives are continuous. Sufficient condition theorem. If the four partial derivatives u sub x, u sub y, v sub x, v sub y exist in an open neighborhood of a point, are continuous there, and satisfy the CR equations, then f is analytic in that neighborhood. The continuity guarantees that the limit defining f prime of z behaves nicely, allowing us to construct the derivative using the linear approximation. F of z0 plus h equals f of z0 plus f prime of z0 h plus epsilon of h. Epsilon of h tends to 0, which is the hallmark of complex differentiability. In practice, when checking a function, we first compute the partials, verify the CR equations, and then confirm that the partials are continuous. Most elementary functions have this property. The textbook examples illustrate how the checklist works. Polynomials: f of z equals z cubed equals x plus iy cubed equals x cubed minus 3xy squared plus I times 3x squared y minus y cubed. The partial derivatives are continuous and satisfy u sub x equals v sub y equals 3x squared minus 3y squared. U sub y equals negative v sub x equals negative 6xy, so the CR equations hold everywhere. Thus, every polynomial is entire, analytic on all of C. Exponential: f of z equals e to the z equals e to the x times cos y plus I sin y. Here u sub x equals e to the x cos y equals v sub y. u sub y equals negative e to the x sin y equals negative v sub x. Continuity is obvious, so e to the z is entire. Trigonometric, f of z equals sine x cos y plus I cosine x sin y. Differentiating gives u sub x equals cosine x cos y equals v sub y. U sub y equals sine x sin y equals negative v sub x, confirming analyticity. Logarithm, f of z equals log z equals ln r plus I theta principal branch. The real part u equals ln r, v equals theta satisfy the polar CR equations on any domain that avoids the negative real axis, the branch cut. Hence log z is analytic on its branch domain but not across the cut. These examples demonstrate the routine of write u and v, compute partials, check CR, verify continuity, conclude analyticity. A real-valued function u of x, y is harmonic if it satisfies Laplace's equation. Partial squared u with respect to x squared plus partial squared u with respect to y squared equals 0. If f equals u plus iv is analytic, then both u and v are harmonic. They are called harmonic conjugates of each other. Conversely, given a harmonic function u on a simply connected region, we can recover its conjugate v up to an additive constant by integrating the CR equations. V sub x equals negative u sub y, and v sub y equals u sub x. For example, let u of x, y equals x squared minus y squared. Compute u sub x equals 2x, u sub y equals negative 2y. Then v sub x equals negative u sub y equals 2y, v sub y equals u sub x equals 2x. Integrating v sub x equals 2y gives v equals 2xy plus c of y. Differentiating this expression with respect to y yields v sub y equals 2x plus c prime of y. Matching with v sub y equals 2x forces c prime of y equals 0, so c is constant. Thus v equals 2xy up to a constant, and the analytic function is f of z equals x squared minus y squared plus I times 2xy equals z squared. This shows how harmonic functions and their conjugates are tightly linked to analytic functions. Explanation: analyticity is a local property. We say f is analytic in a region if it is analytic at every point of an open connected set. However, a function may be differentiable at a single isolated point without being analytic. Their analyticity requires a neighborhood. Such isolated points often correspond to singularities of the extended function. Removable singularity. If f of z is bounded near z sub 0 or the limit as z approaches z sub 0 of open parenthesis z minus z sub 0 close parenthesis f of z equals 0, we can define a value at z sub 0 that makes the function analytic. Example: g of z equals sin z over z is not defined at 0, but the limit as z approaches 0 of sin z over z equals 1, so defining g of 0 equals 1 removes the singularity. The extended g is entire. Pole: if absolute value of f of z tends to infinity as z approaches z sub 0, and near the point f behaves like c over open parenthesis z minus z sub 0 close parenthesis to the m power with m greater than or equal to 1, then z sub 0 is a pole of order m. Example: h of z equals 1 over z squared has a pole of order 2 at the origin. Essential singularity. When the behavior near z sub 0 cannot be captured by a finite order pole, we have an essential singularity. The classic example is f of z equals e to the 1 over z at 0. The function exhibits wild oscillations and takes on every complex value infinitely often in any neighborhood of 0, Picard's theorem. Understanding the type of singularity helps decide whether a function can be made analytic by a simple modification, or whether it intrinsically fails to be analytic at that point. Problem: determine whether the function f of z equals open brace z squared plus z bar close brace over 2 is analytic anywhere. Hint: write z equals x plus iy, z bar equals x minus iy. Express f equals u plus iv, compute the partial derivatives and test the CR equations. Solution sketch: f of z equals open brace open parenthesis x plus iy close parenthesis squared plus x minus iy close brace over 2 equals open brace x squared minus y squared plus 2ixy plus x minus iy close brace over 2. Hence u equals open brace x squared minus y squared plus x close brace over 2. V equals open brace 2xy minus y close brace over 2 equals xy minus y over 2. Compute u sub x equals x plus 1/2, v sub y equals x minus 1/2. They are equal only when 1/2 equals negative 1/2 impossible. Therefore CR fail everywhere, F is not analytic anywhere. Problem: find the harmonic conjugate v of x comma y of u of x comma y equals e to the x cosine y on the domain double struck r squared. Hint: UCR. U sub x equals e to the x cosine y, u sub y equals negative e to the x sine y, then v sub x equals negative u sub y equals e to the x sine y. V sub y equals u sub x equals e to the x cosine y. Solution sketch: integrate v sub x equals e to the x sine y with respect to x. V equals e to the x sine y plus c of y. Differentiate this expression with respect to y. V sub y equals e to the x cosine y plus c prime of y equate to the required v sub y equals e to the x cosine y, giving c prime of y equals 0, so c is constant. Thus v equals e to the x sine y plus c. And the analytic function is f of z equals e to the z, since e to the z equals e to the x cosine y plus I e to the x sine y. Problem: show that f of z equals 1 over z is analytic on double struck C minus the set containing 0, and classify the singularity at z equals 0. Hint: write f in terms of x and y, verify CR, and look at the behavior as z approaches 0. Solution sketch: for z equals x plus iy, f equals open brace x minus iy close brace over open brace x squared plus y squared close brace equals u plus iv, where u equals x over open brace x squared plus y squared close brace. V equals negative y over open brace x squared plus y squared close brace. Compute the four partial derivatives. They exist and are continuous everywhere except at open parenthesis 0, 0 close parenthesis, and satisfy the CR equations, proving analyticity on the punctured plane. As absolute z approaches 0, absolute f of z equals 1 over absolute z approaches infinity, so 0 is a pole of order 1, a simple pole.